our new speaker, Cordian Reiner. In the first week, every speaker introduce himself in the bullet intro, but in the second week, we don't have the bullet intro. So this is I bear a responsibility to introduce Cordian. So Cordian Reiner is currently working as a professor at UIT Arctic University, and he's leading a very important group, algebra group there. Moreover, he's one of the directors of the Lystormer Center at Norway. For the graduate students who are attending this particular SIMPA school, this is really very important to get familiar that Cordian is acting as a pro dean for PhD education at the Faculty of Science and Technology in his university. And other very important responsibility he bears is leading Norwegian Mathematical Council. And let me just tell you that Norwegian Mathematical Council is one of the most important councils in mathematical community. You might heard of the Abel Prize. So he is the member of the board or who decides the Abel Prize. In other words, Abel Prize committee. So his education, regarding his education, he did his PhD in mathematics, completed his PhD in 2011 from the Goethe University of Frankfurt. And along with his mathematical interest, which is quite diverse in the area of algebraic geometry, and he's a very active organizer who is organizing many good activities, many effective meetings in the area of algebra and algebraic geometry. So you can see SIAM meetings in Arctic University and many important conferences, and he is a key organizer. Along with his math research interest in algebraic geometry and commutative algebra, he is also having the interest of exploring mathematical educational studies. So he has recently a very good paper, which is on attitude toward mathematics, achievements, and dropout intentions among the STEM and non-STEM student in Norway. So in any case, this is Cordian is a very good example to follow. So, if you are a mathematician and you would like to contribute in almost all aspects, so he is a good example to follow. This is so unfortunate we could not have him here because his presence would give a different, you can say, the charisma to our school. And in any case, we can't blame anyone because Cordian was very, very, very excited to be here. But there are certain constraints he could not, we could not do anything with. But anyways, having Cordian here online and he's still supporting for his support. We welcome you, Cordian, in this SIMPA school and really appreciate your support throughout the preparation of this particular proposal and your continued support and presence in this SIMPA school. We welcome you. Let's welcome Cordian.
Thank you very much. That's really more than I had hoped of myself to hear. I'm very sorry that I cannot be with you in presence. As was shortly mentioned, I was very unfortunately starting 2024 by rupturing a ligament in my arm, which is not a fun thing to do, and it was a little bit chaos and so. But I'm very happy to see that you're all enjoying the summer school or a winter school in that respect up to this moment. And I would like to talk a little bit about symmetries in the next 4 lectures. So this will be a very exciting tour, I think. But of course, as I'm remote and cannot interact with you in person, this is also very challenging for you to follow explanations that are just giving online. So I'm looking also forward in particular to the Wednesday tutorial when we try to make things that are maybe now a little bit abstract more concrete. So this is very demanding for you to follow so many lectures online. So let's just start into what we will talk about. So symmetry is actually lying at the heart of mathematics. And you all may have seen symmetry in art. So there's a lot of symmetry in art, where you see, for example, here, a very beautiful kaleidoscope. And what these lectures are about is to see a little bit, first of all, what is the language, one language of symmetries, namely we will learn today a little bit the basics of representation theory. And as this summer school or this school, Simpa school, is related to algebra and algebraic geometries, we want tomorrow go a little bit into how symmetries act with polynomials, and symmetries in that respect are called invariant theory. So this will be a very brief introduction into these two main topics, representation theory and invariant theory, in these first 2 days. As I said, this will be a little bit material dense, but I will also provide you with something to read that you can read to follow up a little bit. And I hope that the Wednesday tutorial makes these more abstract things a little bit more concrete. And then on the last 2 lectures, I want to actually use these things in applications, that we actually see that this is not only a beautiful theory that can be understood and help us to understand symmetries, but that it also can be something that is particularly useful for computations. Okay. And whenever you have a question, I feel this is of course very hard from the audience. Maybe I don't know how the microphones are, but whenever you have a question or if anything is unclear, just feel free to unmute yourself if you're remotely, or raise your hand in the audience, and I guess that we can answer the questions immediately. Okay, let's dive into the first part, which is representation theory. Okay, and I want to start with a very, very interesting example, maybe, that some of you maybe have seen before. So this matrix here that you see here, a matrix of this type is called a circulant matrix. And if you use your favorite, so this is a matrix where I assume that these CNs, they are indeterminants. Okay, so you take a matrix, an n times n matrix, and you fill in some unknown entities C0 to Cn minus 1. Okay, now you all have seen that computing determinants can be very important in algebraic geometry. So you might want to use your favorite computer algebra system. I don't know what this is, and I don't want to force you to anything, but you have, for example, seen a Sage could be useful here. If you type this in to this, for example, in Sage, and you want to ask its determinant, something very interesting will happen. So if you compute the determinant of this matrix with indeterminants, it actually will factor into a product of linear forms, and you can actually also look at this, how these linear forms are actually made up. So it turns out that if you look at these linear forms, the coefficients will appear and some roots of unity. Okay, so there is a matrix and there is roots of unities and a very interesting factorization pattern. And the goal of today, and also the tutorial on Wednesday, where we will do this a little bit more concrete, will be to understand why this is actually happening. So, I mean, why this is happening and what this has to do with symmetry. So if you look at this matrix a little bit closer, you may already see that, of course, I mean, there is a specific symmetry pattern happen here. What is the symmetry that I mean here? You see, if I look at the first row of this matrix, for example, it almost identically gets repeated in the second row. However, it gets shifted a little bit. So you see the first row and the second row, they're almost identical, but they are shifted. And so is the third row, the fourth row, and so on. So what this matrix is actually made up is shiftings of the first vector. So this is a very particular kind of symmetry, a very easy symmetry, and easy symmetry will give us an easy factorization pattern of this determinant.
Cordian, this is the same matrix we call the Toeplitz operator, or this is a
I mean,
different one?
it's related to Toeplitz operators.
Okay,
Yes, very
okay.
good. Very good. I mean, but here for me, this is now just a matrix, and it's just a very peculiar thing that if you look at this matrix, suddenly it seems to factor, the determinant seems to factor very nicely. And if you remember linear algebra, which I guess all of you remember a little bit. I mean, there is some sort of diagonalization maybe going on here that is particularly nice, but that actually, this is the important thing, this diagonalization, normally we do for matrices with numbers. Here there is a nice diagonalization that is possible even if we have these unknowns inside. Okay, this is maybe the something to keep in the head of your mind for the rest of the lecture, if you're curious to understand why this is happening. Okay, so this was just the motivational beginning. Let's just give us our little bit more vocabulary. So throughout this lecture, we will always work with groups. So G is a group, and I assume that every one of you has seen a group before. And I take a field, which for the rest of this talk will be an algebraically closed field of characteristic 0, aka the complex numbers, for example. So there is that you can use all of what we're doing today. You can use any field you want, and things become much more complicated. But we will just stick to this very simple setup in the end, where we have a finite group and the algebraically closed field, the complex numbers. Okay, so with this setup, what we have is we take a representation of a group, by which we mean it's a finite dimensional vector space. Again, you can also use infinite dimensional vector spaces, but why not just use for finite cases now? I have a vector space and I have a homomorphism, group homomorphism. I take the group and I map it to the general linear group, aka the invertible transformations of V. So what this means is I have my group. This group lives in an abstract land of groups, and I have a representation which is just a very concrete incarnation of my group as a group of linear transformations on a vector space. Okay, and I mean, I start with a vector space. This vector space has a dimension, and I just say the dimension of the vector space is the degree of the representation. Let me also point out again, so the representation is really the vector space in addition with the homomorphism. So it's always a pair, vector space and homomorphism. Okay, and I can also have a look at two representations of a group. So I have two vector spaces, I mean V and V prime, and rho prime, two representations, and I say these are isomorphic. Well, I mean if the vector spaces are isomorphic, so finite dimensional vector spaces over a field are mostly isomorphic as vector spaces if they have the same dimension. Yes, but now I have an additional property that this isomorphism has to verify, namely it needs to commute with the action of the group. So another way of saying, two representations are isomorphic as representations if the group G acts in the same way on isomorphic vector spaces. Okay. And you all know that if I have a finite dimensional vector space, I can always select a basis. So if I select the basis of my vector space, now things become a little bit more concrete. Select the basis, then every linear invertible transformation on this vector space can be associated with an invertible matrix. So by choosing a basis, I get a representation in matrices. So actually, I realize my group as a subgroup of invertible matrices of if the vector space is of dimension n, of n times n invertible matrices. Okay, so this is a lot of vocabulary maybe, but let's maybe look at some examples to make this vocabulary a little bit more concrete. Okay, so the easiest example, it's almost a trivial example, that's why it's called the trivial representation, happens if we just take a trivial one-dimensional vector space and I associate to every element in my group the one in this one-dimensional vector space, so the scalar one. This is called the trivial representation. Let's just briefly look in our head. So obviously, this is a well-defined group homomorphism, and these matrices that we get in this way are just always the one-dimensional identity matrix, so they're always invertible. Very good. It's a very easy example. Of course, let's take a little bit more complicated example. Let's take a one-dimensional vector space still, V, and a group with two elements. So the first maybe interesting group with two elements. Then I can also assign another representation to this group. Namely, I can say, well, I map my first element, my identity element, I map to 1, and the other element I map to -1. Okay, so you can check that this also satisfies the properties that we have set before. So this also gives a representation of this particular group now. And this is a representation also of degree 1 because the vector space is of degree 1. Okay, we can generalize this a little bit more. Now take a finite set S. Okay, and I have an action of the group on this set S. So for example, this group permutes the elements of my set S. And then I can look at the vector space Vs, which is just the vector space spanned by all the elements of S. So I mean, I take a basis, a formal basis indexed by the elements of S. And then I can define what is called the permutation representation of G, which is just, I mean, I let G act via the homomorphisms that I just define as, well, G acts on my set S. Okay? And this representation is of degree, of course, the size of S. And because the matrices that I get will be exactly, the basis that I have is indexed by the elements of S. And a particular case of this actually happens when I take my set S to be the group G itself. So I have an action, I have a group. The group can act on itself. And if I look at this particular case, then the representation is called the regular representation. Okay, now we have seen 4 very abstract, still a little bit abstract representations. Let's make it even more concrete. Okay, so let's look at the cyclic group of order 5. So this is a group of 5 elements, and you all hopefully remember from linear algebra that this group is generated by one element, G, in the form G to the 0, which is 1, G to the 1, G to the 2, G to the 3, G to the 4. So this is a cyclically generated group. That's why it's called a cyclic group. And because we have one generator, it is enough to know how this one generator is mapped to, and then we can use the fact that the group is generally is cyclically generated to actually get all the matrices for this representation. So we just take our favorite basis B1 to B5, and the group now acts cyclically on these elements. So that means that G, my first element, might be mapped to this cyclic permutation. So you see this is a 5 times 5 matrix, when if acted on by a vector will rightly cyclically shift this vector. And then I have G to the 2, which again gives me a matrix. And in this way, I associate to every element of G a 5 times 5 matrix. So we get a 5-dimensional representation of G, which is now hopefully very concrete. In this case, we could also, of course, assign a 1-dimensional representation to the group C5 by just assigning to every element, to the element G, and henceforth to all the other elements, a root of unity. Okay, so I take a root of unity, a 5th root of unity, I assign G to this root of unity, and then I implicitly already have assigned all the other elements, because all the other elements are just powers of G. So important to remember, and we will come on this again to this example on Wednesday more in detail. We get a group. For this group, we have now seen a 5-dimensional representation and 5 1-dimensional representations. And in particular, of course, if we choose for the root of unity the trivial root 1, then we again get the trivial representation of this 5-element group. Okay. And another example that I wanted to look at is we could also look at the symmetric group. So remember, the symmetric group is a group of all permutations of an n element set. So this is my n elements here. The symmetric group acts by permuting these. So starting, for example, by 1, 2, 3, 4, 5 to n, there is an element in Sn that maps this set, to, this vector 1 to n, to another ordering of the same set. Okay. So this, as you maybe also recall from linear algebra, from algebra, is a group with n factorially many elements. It's a huge group, okay? And this has a natural representation on the vector space Cn by permuting the coordinates. What do I mean by this? So we look at the vector space Cn as the direct sum of one-dimensional vector spaces indexed by the standard basis Ei. And we just define a group action now by saying, well, I mean, I take the ith element of my basis and I map it to the whatever basis element I get when I apply G, the element G to the number one, to the number I. Okay. So this now then extends also, again, if we have a linear map that is now prescribed by every element on a basis. So this actually gives a matrix representation of my group, which I call Mg. So M is a matrix, M of G is a matrix, and that's a matrix. So it's an n times n matrix because it acts on an n-dimensional vector space, and its entries are just 1 if G maps I to J and 0 else. So this is a representation of my symmetric group, where to every element I associate a so-called permutation matrix, namely a matrix with zeros and ones. Okay? So I hope these examples have made the notion of representation a little bit more clear. And as I said, we will come back a little bit to this on Wednesday to understand this a little bit. So if you read the notions in the literature, there is sometimes an equivalent and maybe even more convenient notion of the same thing, which is the notion of a so-called G module. Okay, so it's almost the same thing. It's you take a finite group and a finite dimensional vector space. Again, you can also skip the finite here. And then we say that this vector space is a G module if I can define on it a left G multiplication, which, I mean, satisfies these two axioms, namely that it's compatible with the group. I mean, so that we have, however we multiply, it actually commutes with the group, and it's compatible, the group action is compatible with the linear structure of V, meaning, well, by taking the group element onto a sum is the same as taking the group elements of each of the individual summands, and the group action actually behaves nicely with scalar multiplication. Okay, so these are the two structures that we have in a vector space. Okay. So this is a notion that you sometimes also find in the literature, and it looks completely different maybe at first, but actually, I mean, these two notions are one-to-one the same. So it can be a very interesting exercise that we will maybe discuss on Wednesday to see a little bit that these two are, in fact, actually giving you the same structures. Okay, and if I have two G modules, or I mean, the real advantage of this is that you actually can in the discussion only talk about G modules, and then you don't have to always carry with you the notion this letter rho that is the homomorphism. So that's maybe why people appreciate this notion. So if we say that I have two G modules, what we actually always would write in the other way is I have two vector spaces V and W together with representing group homomorphisms, and this is maybe a much nicer way of writing exactly the same thing. And then all the homomorphisms from V to W that actually commute with the group, so that give us equivalent representations, are called G homomorphisms, and the endomorphisms of V that behave nicely with the group action, they are called the G endomorphisms of V. Okay, again, a lot of definitions for the moment, but let's see this in a little bit more details later. Again, if there are any questions, please feel free to completely jump in. Okay, so there is a very interesting first, I mean, it's not yet the result, but an interesting thing that we will need for the exercises on Wednesday, which actually can be used to characterize representations. That's why it's called the character of a representation. And this is just a very simple map. So it is defined as a map from the group to our ground field C, and is given by, I take a group element, I associate to this group element a matrix Mg, and when I have a matrix, I can look at the trace of the matrix. So remember, the trace is just the sum of the eigenvalues. So this is a number in C, and I can do this for all G in G. Okay, so and the map that I get in this way is a map from the group to the complex numbers. This is called the character of the group. And of course, this looks a little bit arbitrarily defined, because I have talked so much about representations and choosing a basis to make it into a matrix representation. So actually, you might wonder, this is a very not well-defined map, because I mean, here I implicitly assume that we choose something here. And of course, you all hopefully remember that the trace of a matrix is actually not, I mean, the trace of an endomorphism or a homomorphism is not dependent on the base that you chose. So this is actually purely depending on the representation that we have. Okay, so whatever basis you choose doesn't matter, you will always get the same number. So this is why this map doesn't depend on this choice. And one can actually also define an inner product on the space of all characters, which is just defined in this way. And this will be a little bit interesting, because we will talk about orthogonality of such characters. Okay. Again, this was a lot of material to digest. So let's just look at the first proposition for those two things. So if I have two characters, so this is functions from the group to the complex numbers, or to my ground field for two representations. I mean, first of all, what I have is I mean, independent which of them I choose, I have that they give the same number on two conjugate classes of, oh, this should be a capital G here. So conjugate elements give the same character. This is also a very easy exercise that we will maybe discuss a little bit on Wednesday. This just comes from the fact that conjugating with the group action just corresponds to left-right multiplication, and because you can always cyclically shift around in the trace, this will be actually the same number in the trace. And when I look at the character of the sum of these representations, so I mean, I can also take these two vector spaces, I get a new vector space here, and I can look at the corresponding matrices, I build the block matrices, so then the traces obviously are just the sum of the two, and I can also define a tensor product. This is an exercise maybe to show that also the tensor product, you have a well-defined group action, then the characters are just the products. This is all just following from properties of the trace. Okay. Okay, now we have seen representations. So we have seen that for a group, I can apparently define many ways of having the group act. So now the question is a little bit, why is this interesting? And we will see that this has actually something to do with this matrix that we have seen in the beginning. But now I want to invoke a little bit an interesting thing, namely that some representations are maybe more interesting than others. And this is now coming to the first really important definition of irreducible representation. Okay, so again, we have a finite group we have a G module, which is nothing else than a vector space together with a group action. And then we all know that vector spaces can have, they're not the very trivial empty vector space, they can have submodules that are real sub vector spaces. So I take a sub vector space V, and if this sub vector space V is also closed with respect to the group action, so whenever I take an element in W and I have the group act, I get again an element in W, then I say this is not only a subspace, but it's actually a G-stable subspace or a G submodule. Okay, I have a vector space. We know that vector spaces have a lot of subspaces, but now I only look at those subspaces that are closed with respect to the group operation. Okay, so now we say that a module or a representation which does not contain a non-trivial, I mean every vector space of course contains itself, and it's as a vector space itself it will be again a representation, or it contains the zero vector space, which will be also closed with respect to the group action. So if it does not contain a non-trivial irreducible, if it does not contain a non-trivial subspace, subspace that is closed with respect to the group action, then we call it irreducible. Yeah, so makes sense, irreducible. Otherwise, we'll call it reducible. Okay. Is there a question? I'm sorry, I cannot hear the question.
Just wait for a while. Aksha.
Oh, so by irreducible, you mean simple module as well, because the same definition we use for the simple algebra.
Exactly. It's exactly the same thing. I'm actually, yes, you're absolutely right. Absolutely right remark. Yes. So I mean, yeah. So I'm cheating here a little bit, and you will see why I'm cheating. I'm not cheating, but and this is exactly the same notion. Okay. So example, of course, if I have a one-dimensional vector space, I mean, every one-dimensional vector space does only contain either itself or the zero vector space. So by pure triviality, every one-dimensional G module is irreducible. So that sounds really like a boring definition. But let's look at the two-dimensional vector space, where we have the symmetric group. The symmetric group S2 is acting on a two-dimensional vector space by just looking at these permutations of E1 and E2. Then I claim that this representation is reducible. Okay. Now, I mean, of course, this is a two-dimensional vector space, so you might see, of course, it is reducible because I can find a one-dimensional subspace. But the trick is, of course, that I need to find a one-dimensional subspace that is closed with respect to the group action. So we have to be a little bit careful. We cannot just take any one-dimensional subspace. And the one-dimensional subspace that we can choose is just the one-dimensional space that is spanned by the sum of E1 and E2. Because now if you look at the sum of E1 and E2, if my group acts on this, then it will always map this vector to itself, right? I mean, E1 is mapped to E2, E2 is mapped to E1. So the sum of them is just mapped to the same element again. So this vector space is obviously stable. And so we have found a one-dimensional subspace in this two-dimensional space that is also closed with respect to the group action. Okay. Sorry for that. So an exercise that we want to see on Wednesday actually is that every abelian group is for an abelian group, every G module with dimension greater of 1 is reducible. Or another way of saying this is that every abelian group has only one-dimensional irreducible representations. Okay, so we have seen that every vector space can be can be decomposed into one-dimensional vector spaces as a direct sum. Now this can also be done with G modules, and this is the following theorem, which is a theorem due to Maschke. So if I have a finite group and a field of characteristic 0, then every finite dimensional vector space, which is also a G module, is a direct sum of irreducible modules. So, and this is where the notion of simple and irreducible come together again. So it was already hunted into the name of reducible and irreducible. So I take my vector space and I can always span it as a direct sum of these irreducible modules. So every module can be decomposed into irreducibles. So let's just do the proof of that very quickly. So we argue by induction. So if I have a one-dimensional vector space, it is in particular irreducible because we have already seen it only contains the trivial vector space itself or 0. So a one-dimensional vector space that has a G auction on it is always irreducible. So if I have a dimension greater than 1, then either it is irreducible. So if it is already irreducible, then we're done. Nothing is to show. But we can also assume that it is not irreducible. So there is a submodule W that is G stable. So in order to actually decompose our vector space now, we need to define a complementary G module, right? So how do we do that? There is a very, very funny way to do that. A very interesting way of doing that is we define just an inner product on V that is doing the job for us. So we assume that we have an inner product on the vector space. So we have an inner product on this vector space, and we define a G invariant inner product by just the following. So this is something that you will see through the course more often. So I take my normal inner product, and now I just average over the group. So I take every group element and I sum this inner product, I let the group act on the vectors, and I average it out. Okay, so I get a new inner product, which I call with subindex G, which has a very important property, namely, it will be invariant with respect to G, meaning that whenever I have G acting on both vectors here, I will get the same thing back, right? That's just literally how I defined it here. And the important thing now to notice is if I am in the situation, then if I have a non-trivial submodule W, I can consider its orthogonal complement with respect to this vector space, to this inner product. And the claim, which we will maybe discuss on Wednesday, is that then this is actually also closed. This is also G module. And this really just follows from the fact that I just try to hint up here is if I act on F, on V and on W with G, and it's 0, then I will also, then the inner product is left invariant. So if V is in V and W is in W, then whatever I do here, however I let the group act on, will not change the inner product. Okay, so we have now seen that I take a representation, I can always decompose it into irreducibles, and we can now argue by induction, namely that when I have now these two, I mean, they are of smaller dimension, and we can argue by induction that we have already done it by smaller dimensions. Okay. So now we come to the really important notion, and this is a theorem, although it's called lemma. This is Schur's lemma, and this is actually hopefully explaining why the notions that I set up all make sense. Okay, so this is very briefly, it's about two irreducible G modules or two vector spaces together with a group action so that there is no non-trivial subspaces that are left invariant. And then it says that if I find a group homomorphism between those two vector spaces, so a homomorphism between those two vector spaces that commutes with the group action, then the only choices for those homomorphism is that they're either the zero map or that they are an isomorphism. Okay, so in particular, if I take a G homomorphism of a irreducible representation onto itself, it's equivalent to multiplication with a scalar. Okay, so the proof, I mean, just as the sketch now, is actually very simple if you have set up the notions in the way that we had it. And it is just the following. So you take a G homomorphism, so a map from V to W that respects the group action, then one actually can literally easily show that then also the kernel and the image of this linear map are G invariant. So they give rise to submodules. So, but we already assumed that both V and W are irreducible, so that there should not be any submodules that are left invariant. So that actually just leaves the two possibilities. So either the kernel is zero, namely the trivial subspace in V, or the image is the whole thing, namely the whole of W. So then I have an isomorphism. Okay. So important to remember, and this is maybe the single most important theorem that we will need for the sequence, is that whenever I have two irreducible representations, the homomorphisms, the G homomorphisms that map the one to the other are very, very easy to understand. Okay, so let's just see some trivial corollaries of that. So for example, if I have an irreducible representation, then as I just said, the endomorphisms that I have on this representation that are G invariant are just the scalar multiplications. If I have if I have an irreducible representation W and any other representation, I can actually see how often, I mean, the multiplicity of the irreducible representation, that how often does W appear in V by just studying the dimension of the vector space of all G equivariant maps between W and V. And if I have two characters that correspond to irreducible distinct representations, then they will be orthogonally to each other with the inner product that we have defined previously. Okay. So another thing that I will be referring to very often is the so-called isotypic decomposition. So we have already seen now that I can decompose every vector space with a G action into irreducibles. So I can always decompose V into a direct sum of irreducibles. And now if I group the irreducibles in a way that all the irreducibles that are isomorphic, pairwisely isomorphic to each other, are mapped together. So if I look at this vector space, W alpha and alpha is the direct sum over all irreducible representations V alpha, W alpha that are pairwisely isomorphic, then I get a decomposition which is called the isotypic decomposition. So this V alpha is just this direct sum of the W alpha. This is called an isotypic decomponent. And we now get a decomposition of the vector space into so-called isotypic decomponents. And one can show that this decomposition is unique. Okay, so this isotypic decomponents sort of help us to understand how the group acts on a vector space. Okay, and if I now look at such an isotypic decomposition of my vector space, such that the dimensions are di, then what I get is, with Schur's lemma, that this up to ordering this isotypic decomposition is unique. So, I mean, these, just to say again, these WK, how I choose them is not unique. There might be many ways that I've chosen these WK. However, this part in this direct sum is up to ordering whichever number I gave them, 1 to k, is unique. And more importantly, I can choose a basis of my vector space that actually respects this decomposition. So I just choose a basis of my vector space V such that, I mean, I first choose the basis of this one, then I choose the basis of this one, then I choose the basis of this one. So a basis that respects this decomposition gives me a new basis, of course, a matrix representation where my group action is then just, I mean, closed onto this summons. So this is exactly what is writing here, and I get a very special matrix representation, sort of by blocks. And if I look at this matrix representation, I mean, this is given by a basis, a chosen basis, and this basic change gives me an isomorphism, and this isomorphism actually, and this is the essence of Schur's lemma. This basis change actually realizes my endomorphism. So these are all the endomorphisms of V that commute with G as a direct sum of very simple matrix algebras. Namely, here you see this will be block diagonal matrices where the dimension of these is exactly the multiplicities of this. So we will make this a little bit more concrete on Wednesday to actually see how this actually turns out in some examples. So you don't have to remember this formula, but it would be very good to look at this maybe.
Cordian, we can't see the exercise in the previous slide.
The exercise. Sorry, the exercise was just try to figure out the details of this. Yes.
Okay.
So sorry, that was.
Okay. Okay.
So I mean, and again, what does it mean to be? What does it mean to be an? What does it mean? Now let's make it very concretely again. So if I take now a matrix, for this to be an endomorphism, what it means is that this matrix commutes with the notion of with the action of the group. And so if I assume that my vector space decomposes, or my representation decomposes in this way, then actually we can find a basis for the vector space such that, I mean, the basis is given by a matrix T such that I get a new matrix W, new matrix Y, just base change of my matrix X that has a block diagonal structure. A block diagonal structure just means instead of a matrix that is n times n, I have a matrix still n times n, but it has a lot of zeros and it has blocks where it's maybe not zero. It has k blocks. Each of them is of dimension mi/di, corresponding to these irreducible decompositions. And the block further decomposes in di equal blocks of dimension mi. So this is a lot of things to keep in track. So the important thing is just that because I have this group action, I can simplify my matrices substantially. Okay, so in particular, so this is, I mean, so my new matrix will so Y will be having a diagonal here. The diagonal will be these blocks yi, and each of these blocks will contain some repeated blocks in here. Okay. So let me before we come to one example that I want to show you, just again, what is the take-home message? So the important thing is you had a lot of information flowing onto you now that I just threw even through the internet, very unhandily maybe to you. So this is a lot to digest maybe, but what is the important take-home message? So the important take-home message is whenever you have a linear group action on a vector space, there exists a very nice basis for the vector space, and this very nice basis is given to you with the help of linear representation theory, which makes linear matrices that behave nicely, that are compatible with the group action, of course, potentially just much simpler. Okay, so linear action, the group acts on the vector space, you have a basis for this vector space, and you have matrices that are compatible with the group action. And if you have this setup, you can use representation theory to actually make the matrices much simpler. So let me just advocate, there's a very nice book by Jean-Pierre Serre about linear representation theory of finite groups, where you can learn much more on that subject. But I wanted to just briefly give one example, and this is maybe coming completely out of the blue now for the moment, but we will come to that again on Thursday and Friday. Okay, now reset your gears a little bit, and we are looking at graphs. So I have a graph. So a graph is given by a set of vertices and edges, and it is called independent. So a graph is called, a subset of vertices is called independent if there are no elements that are connected by an edge. Okay, so I select some vertices, and if they are not connected by an edge, I call them independent, and the number alpha g, the graph, should denote the cardinality of the largest independent set. Okay, so of course, I mean, the graph is finite. Let's assume there is a largest subset, and I mean, independent just means some of them maybe are dependent, so I will remove them. So there is a largest independent subset of my graphs. And another concept is the coloring of a graph. So I distribute k colors on the vertices of G such that no two neighboring vertices have the same color, or such that two vertices always obtain different colors. And then there's, of course, if I assign different colors to all vertices, I mean, obviously I will get such a coloring, but there is a smallest number k such that there is a k coloring of the vertices. Okay, so two combinatorial things, independent number and the coloring number of a graph. Okay, so let's just briefly see this. I mean, if I take a graph, so this is my graph here. So then I claim that there is, I mean, I claim that there is no smaller independent set than a set of order 2. Okay. Namely, I can choose those two vertices. I mean, they are obviously independent. And I claim that whenever you take a third vertex, I mean, you see, if I take this vertex on top of it, I mean, it will be dependent. If I take this vertex, it will be dependent. If I take this vertex, it will be dependent. So, I mean, locally, I cannot improve this choice. And if you do this choice for all subsets of order 2, you will see that it's impossible to get an independent subset of cardinality 3. Okay, but this is, I mean, this is not very easy to actually do. As you see maybe here now, I really had to sort of hand-wavingly go through all the possible choices that I made here. And I also claim that the chromatic number, that's the largest, the smallest coloring that I need, is 3. So, I mean, I look again, I have 2 colors, 3 colors. There's a coloring with 3 colors such that no neighboring vertices have the same color. And that is actually the smallest that I can get. Okay. Okay, so this is actually very hard normally to look at for graphs. So this is an NP-hard problem. If you have a graph, compute these two numbers. So now there is, we have already quickly talked about the Abel price, and in that respect, I should actually mention that I'm not responsible to select winners of the Abel prize. I'm just responsible to help that the prize organization. But in the Abel prize, there was 2 years ago a winner, 3 years ago a winner, namely Laszlo Lovas, and Laszlo Lovas actually defined something very interesting. So he defined a matrix for a graph, for an independent set. He defined a matrix which is defined here. So this is just taking the indicator function. So the indicator function is 1 if an element is in a selected set, or 0 if not. And he defined this matrix in this way. So this is just the direct, this is just the product of the indicator function of a set S. I mean, this is now a little bit maybe still abstract. So he looked at this matrix and he realized that this matrix has two important properties. Namely, I mean, if you sum up over its diagonal elements, of its elements, it gives you back the size of the set S that you started with. And this matrix is always positive semi-definite. So this follows really just by definitions of this construction. And what he realized is that he can use this to define a problem which he called the theta number of a graph. So the theta number of a graph is just so you try to maximize this over all matrices that are positive semi-definite and that have a certain property on the edges of the graph, which is here. You try to maximize the size, which is given by this. And this is called the theta number of a graph. So this is now a little bit, I mean, coming completely out of the blue, and you don't have to completely be with me for the definition. But the important thing is this theta number is easy, can be calculated much easier than normally the theta, this quantity alpha and of the graph. So the interesting thing is that what he could show is, and this is far from trivial, is that actually this theta number that I can compute with the computer much easier has the nice property that it upper bounds this independent number and lower bounds the chromatic number of the complementary graph. So I mean, it sort of gives me a sandwiching. It gives me upper and lower bounds for these numbers that I otherwise are hard to compute. And actually, Lowas also could show that for a specific class of graphs, this actually gives the right numbers. So why did I show you this? So I just want to come back to one small example. So assume we have a very simple graph. So this simple graph is just given by 4 vertices, and they're cyclically ordered in that way with arrows. Okay. So it's very easy to see that this graph has a natural action of the cyclic group of order 4 on it. Namely, I just switch the labeling of my vertices cyclically. Okay. So so if we then use, I mean, this whole theory that I have not really completely you maybe have not really completely digested. So I take the 4-dimensional vector space C4, I find a specific basis, which is the so-called Fourier basis, which is related to the matrix that we had in the beginning. Then I can actually simplify this program by to come up. So all the conditions that I have, all the matrices that I will have, are now diagonal matrices. I have these elements in the diagonal, and all the conditions that I previously wrote down become very simple to check, and one can actually calculate this theta number explicitly and express it in these very nice cosine expressions, which, I mean, if you remember, relates a little bit to this rules of unity. So we will do this. We will try to solve this exercise together on Wednesday to see how these notions of representation theory help us in a very concrete example to simplify matrices and how this can be actually very useful to calculate something. And with that, I want to almost close. So you already see behind me this beautiful green display of Northern Lights. So I took this picture here that you see here last night when I was preparing for this lecture and couldn't sleep because I was a little bit nervous. What you see is Northern Lights. So Tromsø is a very beautiful place to do mathematics, but it's also a very beautiful place to see these amazing incarnations of beauty on the sky every night in the winter when the sky is clear. So with that, I thank you very much for the attention, and I hope we have time for some questions.
Thank you very much. Thank you, Cordian. Are there any questions from the audience? So it was It was loaded with lots of definition and dictionary. And for the participants who are participating online and everyone, we are recording every lecture, and we are putting all these lectures on the website. If you missed any, and if you would like to see any definition once again, so you can download the video and just do the rehearse of drill of these definitions. So, are there any questions from IBA Karachi?
Yes, I have a question.
Yeah,
So I
please go.
want to ask that are quiver representation are somehow related to group representations?
Say again, I didn't hear the first one, sorry.
Are quiver representation are related to somehow
River
group
representations. Oh, that's a very, very good question. So, I mean, they are related in spirit, I would say. I mean, this. I mean, you can. I mean, for every algebraic object, I mean, you can look at representations in that sense that make you this representation more concrete with vector spaces and homomorphism. So, in that sense, they are related. And I mean, I
Okay.
know too little about quiver representations that I want to say anything more that would embarrass me. And
Okay, thank you. This is not a nice picture.
Yeah, these are.
so exactly, I mean, there's many things you should take home, and many things you should digest. I mean, this picture is amongst the things you should take home in your memories.
Okay, are there any other questions or comments from the audience side?
Just
Yeah.
perhaps a comment. Quiver representations are more related to representations of algebras than groups, I guess.
But it's this, I mean, so it's that's why thank you for this comment. This is why I was happy not to say more. But I mean, in theory, the representations of algebras are very much related also to representation. I mean, in spirit, they're all related, right?
Yeah, in spirit, yes.
Okay, if this is there are no more questions, let us thank Cordian, and please keep posting these Northern Lights Aurora for all the participants every day with a fresh one. Let us thank Cordian. Thank you very much.
See you
It is
tomorrow.
too early. It is too early for Cordian to get up and deliver these lectures, and we will keep him awake throughout the week. Okay, Cordian, you can take your
Exactly. But
breakfast now.
luckily, I already had a coffee, so that was helping me.
Yeah. Thank you. Okay, an announcement for the participant now. It's the lunch break, and please be here sharp at 2:30. We have another speaker from US, Aida Miraj. Today she's also starting her course. Okay, bye bye, Cordian. We'll see you tomorrow.
Bye bye.